Hello. For today, our lesson will be about family of curves. So first, let me define what is the family of curves. So, family of curves is a lesson in differential equation at which we are dealing with standard equations such as conic section, line, hyperbola, and many more. And to get the general solution, we must apply the elimination of arbitrary constants that will be possible by the given parameters in the problem itself, where we analyze it to get certain functions and apply specific conditions. So what do I mean when I say we must get certain functions and apply specific condition? So, for example, find the differential equation of straight lines through the origin. So, the problem describes the equation of straight lines through the origin. So, when we recall, during our pre-calculus days, there are three forms of equation that describes straight lines. First is y is equals to mx plus b, which is the slope-intercept form. Next is y minus y1 is equals to m quantity x minus x1, which is the point-slope form. And the third one is ax plus by is equals to c, which is the standard form. So to execute the solution for this problem is we must choose the best equation that suits the problem itself. So to do so, we must infer to the given information from the problem. So as you can see, we already deciphered the straight lines, which is these three equations. And to choose, we need to choose one equation, obviously. So what is only given is straight lines through the origin. And it only means that our y-intercept will be equals to 0. Okay? Or b is equals to 0 when we take the first equation into consideration. And as you can see, when we set this equals to 0, what we will be left with is equals to y is equals to mx. However, if we use the second equation, there are a lot of parameters that we must consider. y1, x1, okay? As well as the standard form. So we rule out these two equations. We will use the first equation. So for the solution, okay, we use the first equation, y is equals to mx plus b, at which b is equals to 0. We substitute y is equals to mx plus 0. As you can see, we are already done in this part. Get the certain functions and apply specific condition. So the next thing that we must do is to apply the elimination of arbitrary constants. Okay? So to do so, first step is to identify how many arbitrary constants are present in the equation. As we can see, the arbitrary constant at this particular equation is equal to m. It's only m, I mean, okay? So there is only one arbitrary constant, therefore we must differentiate this equation by a single time. So let's do that. That would be dy, okay, over dx is equals to m. And as you can see, we can already substitute this m onto our working equation to get the general solution. So substitute, mark this as equation 2, and mark our working equation as equation 1. So let's substitute m into our uh, working equation. Y is equals to dy over dx, okay, multiplied by x. So to simplify this further, what we must do is to multiply both sides by dx. Therefore, this is y dx, and we transpose this to the other side. Therefore, we get negative x dy, which is equals to 0. And there you have it. That would be the final answer for this particular problem because the arbitrary constant was already eliminated from the equation. Okay, answer. So moving on, let's proceed to our next example. Straight lines through the fixed point x, h comma k, h and k not to be eliminated. So to solve this, we must understand what the problem is actually uh, saying to us. So straight lines through the fixed point h comma k. So straight lines. So in a Cartesian plane, okay, suppose this is the Cartesian plane, we have a fixed point. Uh, for example, this is h comma k, and we need to find the family of lines that passing through the fixed point. So what it only means is this one. Okay, this line could also represent the equation, also this line, and so on and so forth. So again, we are given with straight lines. So we must go back to our previous example wherein there are three uh, forms of equations that we can use. So as you can see in the given, we have x and y. This is x and this is y intercepts that are given from the problem. So the equation that we must use is this one because we have x and y intercepts. So this is the best equation that suits the problem. Okay, so let's use that. So for the solution, that is y minus y1 is equals to m quantity x minus x1. So we substitute, okay, y1 is equals to k and x1 is equals to h. Okay, so this will be equals to y minus k is equals to m quantity x minus h. Okay, okay, so we already identified the suitable equation for the problem, and we already applied the condition at which the fixed point h comma k. Okay, so the next thing to do is to apply the elimination of arbitrary constant. So the first thing that we must do is to identify how many arbitrary constants are present in the equation. As you can see, we have y minus k is equals to m quantity x minus h, okay? But h and k not to be eliminated, meaning the only arbitrary constant that we must consider at this particular equation is again m. Okay, so we only have one or a single arbitrary constant, therefore we derive the equation by a single time. And we already knew that m is actually equals to the slope, okay? And the slope of equation of a line is equals to the first derivative, okay? So dy over dx will be equals to m. So how can we check it? So if we derive this equation, let's mark this at equation 1 as equation 1. Y minus k is equals to m. So derivative of y, when we apply differentiation, dy, for y, this is dy, and for k, that will be equals to 0 because k is just a point in a Cartesian plane, therefore it is has a numerical value or a constant. So for the derivative of k, that will be equals to 0, and m is the slope that has a numerical value, but at this case, we define this the slope as dy over dx. So when we differentiate this this one, this will be equals to dx minus, and h is again a point in a Cartesian plane, therefore 0. Therefore, dy, we divide both sides by dx. dy over dx is equals to m. So that was correct. Okay? And we need to insert again this equation number 2. Let's mark this as equation number 2 into our working equation. And our working equation is the first equation. Y minus k is equals to m times x minus h. And again, m is equals to dy over dx. dy over dx. This is x minus h. We did this because the instruction in the problem is both h and k should not be eliminated. So again, we multiplied both sides by dx to simplify further. Therefore, we have y minus k dx is equals to x minus h dy. We transpose this to the left side. We get y minus k dx minus x minus h dy is equals to 0. That would be the final answer for this one. Our example number 2. So find the differential equation of circles with center on the x-axis. So this figure represents the problem that we have on example number 2. So as you can see, it is actually a family of circles that are located in the x-axis. And if you recall, the center of a circle is located at somewhere at h comma k. But at this particular problem, the center of the circle was located at the x-axis. Therefore, our k at this particular example will be equals to 0. Okay, and the best suitable equation for this particular example is x minus h squared minus y minus k squared is equals to r squared. This is plus. Okay, so we already choose the suitable equation. The next thing that we must do is to apply the condition. Okay, the center of a circle was located at the center of the x-axis. Therefore, this would have equivalent value of h comma 0. Therefore, we substitute for k. We substitute 0. This is x minus h squared. This will be our solution. Plus y minus 0 or y squared is equals to r squared. Okay, we are already done with the steps of choosing the equation and the application of the condition. Therefore, the next thing that we must do is to apply the elimination of arbitrary constant. Okay, so to do so, we must first consider, or we must first look on how many arbitrary constants are present in this particular equation. So as you can see, r squared is an arbitrary constant and h. So we must differentiate this equation by two times. So let's get started. We differentiate this one. This is chain rule. This is 2x minus h copy times the derivative of inside. The derivative of inside is dx minus the derivative of a constant is 0 plus chain rule again 2y copy the inside, and the derivative of inside is dy is equals to the derivative of constant. Okay, reduce is a constant, therefore this is 0. Again, simplifying further, we can divide this both sides by 1/2 by 2, and okay, we get x minus h dx plus 2. Okay, this is y dy is equals to 0, and we can again isolate dy over dx by dividing both sides by dx. Okay, we get x minus h is equals to y dy over dx. Okay, we transpose this to the other side. Okay, we are done with the first differentiation. Next, we proceed to the second differentiation. So, to do so, okay, we differentiate this. This is dx minus 0, which is equals to, this particular term is actually a product rule. This is u and v. And for product rule, this is equals to u dv plus v du. Okay? So, let's copy u. This is negative y times the derivative of v, which is dy over dx, or the second derivative. This is dy squared over, what I mean is d squared y. So this is d squared y over dx squared, okay, plus v du. So what is v? V is dy upon dx, and multiply it by the derivative of u, which is negative y. What is the derivative of negative y? This is simply negative dy, okay? Dy. But there is actually a correction. This should be dx only. So we transpose these terms to the left hand side. Therefore, we get dx plus y, d squared of y over dx plus dy over dx multiplied by dy, which is equals to 0. And again, we divide both sides by dx. And so we get 1 plus y d squared of y over dx squared plus dy over dx multiplied by dy over dx, which is equals to 0. And we can represent this particular term, the second derivative, okay, as y double prime, okay, and uh, this only represents This is 1 plus y times d squared y over dx squared is y double prime. Okay? Plus, and dy over dx is the first derivative. Okay? Multiplied by first derivative again, which is equals to 0. Therefore, the simplest form that we can actually get is y double prime by the virtue of linearity, okay, plus y prime squared, okay. Uh, of course, the constant will be our last term, plus 1, which is equals to 0. There you have it. That would be the final answer for the example number 2. Okay? Thank you for watching. I hope you learned something from this video, and please leave a like and subscribe to our YouTube channel. That's all. Thank you. Rufus boy, let me love boy, what you know. Rufus boy, let me love.